How's it going, everybody? Welcome in. How's the summit going for everyone? Pretty solid, cool. Quick housekeeping thing. We'll probably run the full length of the session here, so for any questions, we got to turn the room over, so just step outside and ask Andrew and Olivia questions out there. But yeah, excited to announce or introduce Andrew Clark from Red Cross Lifeblood and Olivia Wren from Databricks to talk to you about Lakeflow Connect. So pass it over to them.
For joining us this afternoon. So we'll be talking about from Data Vault to Delta Lake, streamlining data sync with Lakeflow Connect. As a bit of background about Lifeblood, as there's a lot of people in the room we may not have interacted with this in the past. We're funded by Australian governments to provide life-giving blood, plasma, transplantation and biological products, including breast milk and fecal matter transplantation, to deliver world-leading health outcomes. We have close to 3,800 people working at Lifeblood, from our donor centre teams who support our generous donors who give, to those in our manufacturing and quality teams who process blood, plasma and biological materials safely. Our many scientific and testing teams who ensure our products and services are world leading and safe, and our various support functions across so many areas, as we all work together and ensure we deliver a world-class, efficient and effective blood service for the health of our community. We operate across 112 sites Australia-wide, and Lifeblood serves over 27.6 million people stretched across 7 million square kilometres. Ultimately though, our more than 610,000 donors are our lifeblood. Without them, we couldn't deliver critical health services to our nation. It's the generosity of these donors that drives us to continually improve our world-class capability. In the last financial year, we have booked more than 2.5 million donation appointments, resulting in 1.6 million life-changing donations of blood, plasma and platelets. Every day, we welcome collections from thousands of generous donors that provide a gift that can be replicated. Of course, every single donation that we receive is life-changing, but just to give you a further quick snapshot, in the last financial year alone, Lifeblood has collected, processed and delivered over 4,000 litres of breast milk to feed vulnerable babies, delivered almost 1.1 million fresh blood products to support Australian hospitals and healthcare providers, and supplied 869 tonnes of plasma to be fractionated by CSL Behring to then be turned into life-saving products to change the lives of patients. Everyone across our organisation works tirelessly every day to support the Australian healthcare community, and our team in particular is dedicated to underpinning Lifeblood's purpose of turning life-giving donations into life-changing outcomes by using data and analytics to drive improvements, measure performance and provide insights to every business unit in our organisation. Within Lifeblood, we work as a centre of excellence for analytics, insights and machine learning, meaning we have the privilege of assisting analysts and subject matter experts with their analytics needs across the organisation. Some examples of the types of analytics projects we provide are using cellular segmentation models to detect specific cells or to detect and measure red cells. We also support a variety of early trials into business as usual initiatives, such as Lifeblood Gifts, our rewards program for donors, and initiatives to improve the donation experience, such as live times, wait time predictions, a trial solution that we ran in previous years to add value to the donation experience by using predictive analytics to anticipate delays and notify donors of any wait times before they arrive in the donor centre. We also support the analysis and planning of our 108 site donor centre network through geospatial analytics to support our teams to ensure our collection network is reachable and effective for donors. Lastly, we provide an extensive catalogue of analytics dashboards and other statistical analysis reports to support our Lifeblood purpose. Of course, underlying all of this is data governance and data availability to drive these initiatives and projects. So today I'll be talking about a component of the next stage of our data platform, which is, as the talk started off, syncing a Data Vault Azure SQL Server data warehouse into the Lakehouse. But to get to that point and to provide balance the decisions and explain some of the constraints we're working under, I'll need to start with some context. At Lifeblood, we've been using Databricks for around 5 years now, Initially, it was primarily for us an advanced analytics, machine learning, and data science platform, but the scope has grown, as have the data teams that use it, including our data engineering teams who use it for their near real-time data processing, particularly for operational technology and regulatory validated pipelines, and analysts across R&D, business intelligence, finance, and other analysts in other business units, including marketing, use the platform in similar ways that we do. But as a result of that growth, we operate under a distributed governance model in our Databricks platform, and where there are items that overlap across boundaries, we collaborate closely with our colleagues to develop the best solution to support not just our team, but the analysts and users across the organisation. The solution we built and we'll discuss today was a result of that collaborative process with the overarching goal to make our Datavault warehouse available in Databricks for all users in the lowest friction, highest capability way possible. The Datavault warehouse we are working with is a modern, high-quality implementation and integrates and combines some of Lifeblood's most core applications data. It has built into it over a decade of established business process and logic, and is a highly trusted and relied upon component of our data platforms. It was critical to the next stage of our data platform to bring our Datavault warehouse and our Lakehouse platform together. So, going beyond that headline goal of making Datavault data available, what did we actually need? What were the requirements for the team? Really, to support the analytics, machine learning, AI workloads on Azure Databricks, we needed a replica or sync of the information layer, which is the equivalent to a gold layer in Datavault, from the SQL Server Datavault data warehouse. And some of the technical requirements is that we need to be able to support daily and intraday sync at minimum. And intraday for us is typically an hourly refresh. Timeliness, so the first sync of the day had to be achievable within 2 hours to meet our start of day processes, and would need to, as the Datavault warehouse wasn't initially designed for this load, so we'd want to ensure that we had predictable and manageable load on source to not cause any upstream impacts. As we're effectively making a replica of a trusted source, we needed to be able to maintain the quality and with accuracy and completeness certainty. And we had some certain constraints around scalability. So we expected that at a field build out, this would be 300 plus information objects or 2,000 plus raw vault, business vault tables. And that's a subset of the overall Datavault warehouse that we have at Lifeblood. We also determined that full change history would not be required, as point of time, latest of time of sync is sufficient in terms of the data that we bring into the data lake. If possible, we'd like more frequent sync, who wouldn't? It's always good. Integrations into Unity Catalog and our existing processes, including DLT. Integration into Unity Catalog observability, particularly for error detection and downstream pipeline recovery. And we also needed support for schema evolution because we expected those tables to change from the source quite regularly. So we, at minimum, needed new columns to come through schema evolution. Lastly, we had sort of the constraints around our implementation. As the overall goal was to reduce the complexity of access to data, that was always going to be a key driver. But we also had to achieve this project within existing headcount and skill sets, with potentially some skill up within the team. And somewhat of an important note is that we're primarily an analytics team. We're not an ICT team, we're not an IT team, we're not data engineers. So it had to be manageable for our skill sets. We also needed the ongoing effort beyond the initial project for tables changing at source to be manageable and a business as usual only effort. And lastly, it was really important to us where there was sync failures that there would be a straightforward recovery from failures. So from that, we took away those requirements and we evaluated the connectivity methods available in Databricks and the CDC capabilities of Azure SQL Server. We assessed our options and essentially we committed to exploring at minimum 2 POCs to an initial trial. However, before we go into the technical evaluation, I'll hand over to Olivia to talk more about Datavault and how it's normally implemented on Databricks.
Yeah. Hi everyone. So Datavault 2.0 pattern on Databricks follows the enhanced medallion architecture. So data is flowing on the screen through several layers. So first of all, starting from the bronze layer, you have your staging, landing, ingestion layer. So here you have data ingested from the raw source layer, and also this data is being served as one source of truth, and you're enabling that for the full auditability and traceability. And following by that, we have the silver layer. So in this layer, we have Raw Vault and Business Vault. So Raw Vault, your data model is being constructed into the hubs, links, and satellites. Hubs are your business keys, and links are your relationships. Satellites are your descriptive data. And then in the Business Vault layer, this is where your business rules and your data quality checks has been applied. And optionally, you can choose to create pointing time table and bridge table to help you for further analysis. Finally, when we're reaching the gold layer, which is also the presentation layer, in Datavault pattern, we call it information mart. So in this case, we're creating the customer-centric views, typically in views, for the reporting purpose.
Thanks, Olivia. So in our technical evaluation, we needed to consider our options and seek a solution that would be fit for purpose for the next 5 years. And to meet that complexity constraint, we initially looked at options within our current tools and platforms as of November 2023 when we kicked off this project, as a preferred option, with custom or external tools being a secondary consideration only. At the time, we had the following options. Firstly was raw only, so this would be just reusing the raw landed data from our existing data vault and redoing everything on top of that. So this would be effectively a full migration and replication away from SQL Server. This would involve significantly more effort than would be achievable within this project, and it was well outside the constraints of this initiative. So that wasn't really on the table, unfortunately. So the second option we looked at was JDBC, which we already used within Databricks quite extensively. This would be accessing the IAM information mart layer directly from Azure Databricks. This was a potentially viable option for our power users, but fell a bit short in terms of the ease of access for regular analysts, and for that we sort of thought it wasn't achievable. The third option we considered was Lakehouse Federation, which had recently been released at around that point. This technology would actually suit quite a few use cases with smaller databases and warehouses, and it was a big improvement on ease of access and integrations within Databricks and Unity Catalog. But we had some concerns about performance and particularly the predictable and manageable load on source and the complexity that would be introduced for the analysts that would need to accept their queries being pushed down to the SQL Server and understanding what that impact would be and what the performance would be. Lastly, we considered a way to build a custom watermark-based CDC and run through Azure Data Factory. This would have been potentially view-specific, and while possible, we thought this would be a lot of extra work to set up. Maintenance would be difficult, and recovery from sync errors was going to be quite tricky in some cases. So none of those options we had natively in the platform at the time were quite meeting what we needed, so we kept looking, and we ended up with a pragmatic solution to use Azure SQL change tracking, and that's where we get to here. So the decision was essentially, rather than trying to directly bring in the information mart or starting over with the raw data from scratch, we explored replicating the silver layer, so the raw vault, business vault model data, which appeared quite possible with change tracking from Azure SQL Server. At the time, the feature that would be eventually known as Lakeflow Connect was just starting to be mentioned in Databricks product roadmap. But in advance of that being available to us, we built a basic change tracking ingestion process to fill that capability gap and allow us to build up the rest of the process around it in advance. The largest change from the previous approaches, which focus on moving IAM directly, is that rather than replicating that IAM layer views from source, would instead sync raw vault, business vault, and then translate the T-SQL views to Databricks SQL, which introduces some complexity there. On the Azure SQL Server side, there would be some additional load on the warehouse due to storage of the changes on targeted tables for the retention period. We're generally running a 7 days retention period for change tracking. But the way that our change tracking works is it also uses a technology we were already using within SQL Server, which is SQL replication, it just redirects those changes into change tracking tables in addition. So the performance load we thought would be quite manageable. And additionally, querying the data out, because we're only pulling out the changes since the last sync, the query load would be much less than directly querying information mart, and would be really predictable and consistent because it would be in line with the amount of rows that they changed each day. So the overall architecture involved 3 main components, which we'll go into further detail in the following section. The initial driver of this is really the view extraction, conversion, and validation process, in which we use JDBC to retrieve the view definitions from SQL Server. So we're always in sync with what they're defining within SQL Server. Then we use a process to extract the table dependencies from the view, and then we convert the T-SQL to Databricks SQL and re-register the view within Databricks. The extracted table dependencies are then passed to the data replication process, which is Azure SQL change tracking and Lakeflow Connect, and we run a separate process for data validation utilizing Lakehouse Federation, Lakehouse Monitoring, and some reports and dashboards we've built up to validate that our data is in sync with our existing data warehouse. Internally, we refer to this combined process as Brickout. So stepping into that view extraction and conversion process, which is that repeatable approach that isn't a once-off migration. We'll have to do this over and over again as the views might change over time. This was to convert our T-SQL to Databricks SQL and prepare the required tables list for Lakeflow Connect. The key way that this run is essentially we've got a YAML file, which is a list of views, and that drives the whole process. So that makes calls back to Azure SQL to extract the view definitions and removes any characters that are invalid for Databricks SQL. It then extracts the required tables using regex from the view, and we only enable change tracking and set up sync for the necessary tables to minimize the compute storage load on Azure SQL. This also has the side effect of reducing the number of Lakeflow Connect gateways and ingestion pipelines we require, because the current recommendation is around 1 gateway and ingestion pipeline pair for every 250 tables that you want to ingest. For that list of tables, we then check whether change tracking is already enabled by querying back to the database. And if it's not, we then check for the prerequisites for change tracking. For us, this is mainly whether a primary key is set. In addition to the view definitions, which are output from this process, we also output a list of tables that are not enabled and the prerequisites are not met for investigation and remediation with the data warehouse team. The tables that we need to have enabled, which we then pass to our DBAs in an automated process, which then they pick up, set up change tracking on the tables and apply the permissions we need to be able to read it. And the tables to be synced, which go directly to Lakeflow Connect. On this slide, I've included a view translation example between Azure T-SQL and Databricks SQL, so our original view and the translated version. For Datavault, we've found with working with a number of views now that it's actually reasonably straightforward to translate because of the structured nature of Datavault and the consistent table structures. So we still have to do something, and we can get away with using LLMs in some cases to speed this up, but we essentially parameterize the create and schema name so that the translated view can be used where needed and applied across different catalogs and schemas. We do a function rewrite of any T-SQL specific functions to Databricks SQL. In the example slide, we've converted from cross-apply to join lateral. And then we also, to give us some extra capabilities out of the replica, we put our point in time controls so we can easily add start of day, start of week, start of month, yesterday point in time views using delta time travel. So this is essentially just appending a time step as at to the views as appropriate. And within Unity Catalog, we structure our synced version. So we've got Brickout, which is our control files and our validation tables and our staging volume. And then we structure the rest of the schemas similar to what you'd normally do in SQL Server with Raw Vault, Business Vault, Information Mart. And in addition, we also create schemas for point-in-time views registration. All right. So where we've got the tables, we've got the view definitions, and we pass them across to Lakeflow Connect to complete the data sync. So as Lakeflow Connect wasn't available when we started this project, we built an initial POC using a custom Databricks work process. Even in a minimum viable product state, it introduced significant complexity to Brickout. It was designed initially as a batch process and would have been difficult to change that to be a high frequency sync. And overall, we felt it would require significant additional effort to meet our medium to long-term requirements. I'll go into the extra steps of the POC implementation included in a very brief manner because this is now being retired out of our solution. But essentially, for each of the tables that we're looking to sync, we would get the current version from Azure SQL. It would then detect the primary keys from the tables, as we'd need those for merge statements later on in Unity Catalog. It would then retrieve the minimum valid version, effectively the minimum version of the Databricks copy needed to be up to sync accurately. And then it's just a simple if statement of whether the minimum valid version is less than the latest sync version or not. If it was true, would initiate an initial snapshot of the table, writing that snapshot with a create or replace table into Unity Catalog. And if it was false, we were certain that we could get the changes needed to bring the Databricks version up to the latest update. So we'd write those changes into Raw Vault and Business Vault using the detected primary key as a merge into. And then lastly, to finish off the process, we update the latest sync version to the current version at the time of sync, and we're ready to run the process again. As a contrast, setting up the data sync via Lakeflow Connect using the UI, but this can also be achieved through an API process, either through the SDK, asset bundles, or the CLI, is a once-off config of an ingestion gateway. Then you can add tables to the sync as required. You also need to set up a destination catalog and schema, and then the initial snapshots and the streaming updates are handled in the ingestion pipeline for you automatically. In terms of how we run it in our environment, scheduling is handled the same as any other Databricks workflow and pipeline. And for maintenance, some schema evolution is supported, but for other changes, when there is a sync issue, it just requires a full refresh of that table from the pipeline, so it's really easy to recover from an error. I'll hand over to Olivia now to give us a more general background on the custom versus Lakeflow Connect change data capture and change tracking syncing in Databricks.
Yep. So before Lakeflow Connect, as Andrew's team experienced, engineering team normally needs to combine multiple tools to achieve this, to bring the data from SQL Server to Lakehouse. So as an example, a general pattern would look something like this. So I would have an extraction tool that is running on a virtual machine somewhere, and then that means I need to think about what infrastructure I need to allocate for that, right? How do I scale for it? And in terms of the software, how can I make it up to date? And following by that, I might create a message bus that needs to subscribe to all the events from the source tables. And later on, I also need to create custom codes in my notebooks, right, to use structured streaming to load the data into the data tables. While this solution works, it will probably going to take me a long time to set it up. And also, I need to worry about the ongoing maintenance about it. And if anything goes wrong with initial source APIs, right, this whole thing could entirely break. So now, with Lakeflow Connect, I can forget about all that complexity in the previous slide. All I need to worry about is what data I want to bring to the Lakehouse. So how do we do that? From a technical level, how do we bring the data from outsource external databases to Lakehouse? Is going through the following steps. So starting from the step one, the ingestion gateway using a classic DLT job is going to collect the credentials from UC, and then using that credential to connect your database and collect the data and save them and stage them for the latest version into your Unity Catalog volume. And from staging, you're using the serverless DLT pipeline to actually digest the data, putting the data into a streaming data table. So in this process, there are three critical entities here. So we have the ingestion gateway, we also have the Unity Catalog in the middle, the volume, and also the managed ingestion. The first one is the ingestion gateway. The gateway is a separate pipeline that captures the metadata, the snapshots, and the change logs from your databases, right? And then that stage the data to the UC volumes. The UC volumes is secured using the same mechanism that you would use for other UC volumes. And from the staging, the ingestion pipeline then collects the data, grab the data, and merge it into the streaming tables. During this process, real-time data replication finds the latest changes using the SQL Server change tracking, CT, if the primary key is presented in the table. If the primary key is not presented table, then we're using change data capture, CDC. We're also locking down the permission by default. That means only the people who have access to this pipeline would be able to run this pipeline.
Thanks, Olivia. So the last part of the process we really need to cover is data validation. So we achieved that through using Lakeflow Monitoring, Lakehouse Monitoring and Lakehouse Federation to snapshot and validate our Unity catalog gold layer and compare it to the Azure SQL Server information mart. The Lakeflow Connect ingestion sync of Raw Vault and Business Vault, obviously that's built on top of some really well-established technologies in terms of Azure SQL change tracking. It's been available from Azure SQL Server for a number of years now. So we're pretty confident we're going to get good data out of that and we'll be up to date. However, as we were converting information mart views from T-SQL to Databricks SQL, that process and its manual and automatic components could introduce errors and data mismatches between our environments. So this process is really to provide a check that we're in sync. So we used Lakehouse Federation as another connectivity method back to the Azure SQL Warehouse to create a baseline snapshot for comparison from information mart in Azure SQL Server. We'd then snapshot from the Unity catalog IAM views into a validation table at the same point in time. This is necessary because Lakehouse Monitoring can't be run directly on views, it needs to be a table. We'll then use Lakehouse Monitoring to compare and create metrics for the baseline versus validation comparison. And as part of that process, it auto-generates a Lakeview dashboard for exploration of those metrics. However, for our use case, we also built an additional custom validation report to check specific requirements and thresholds for our data quality that we use for our decision making about view promotion between environments. On this slide, I've included an example of a monitor dashboard. This is the dashboard that's automatically created when a monitor is run or updated if it's already existing. And this particular one is an example of a monitor dashboard for a snapshot table. The left side of the dashboard provides a list of metrics and statistics used in the tables, and these are generally null value checks, distinct values, those sorts of like overall statistical tests that you can then check to see your data as a overall is the same. The data validation report we built in addition to that, it still uses the metrics from Lakehouse Monitoring, but we do some additional processing. We have flexibility to add additional things on top if we need to. This report, which I've included an example of on the slide, is an offline static HTML output. That was key for us because it allows us to have a stored validation of particular milestones within our development or at particular points in time that we can take offline and store for long-term validation. And it also lets us set up our consistent threshold and rules for reporting. We built this on top of an open source package called Data Validator that we'd used before for a couple of other use cases, so it was pretty straightforward for us to adapt it. However, this and the previous bit of work has only really scratched the surface of Lakehouse Monitoring, so I'll hand over to Olivia now to speak more about the capabilities there and what will be likely to adopt in Lifeblood in the near future.
Thanks, Andrew. So Lakehouse Monitoring monitors all the tables in your Lakehouse. For different types of the tables, we will have the statistics being calculated for the quality of the data in different elements of the table. For example, if you're having a snapshot tables, the data quality matrix is calculated across all table with all the columns. If you're having time series tables, the data quality matrix is calculated across the time-based windows as well. And you can also, moving forward using machine learning models and having Lakehouse Monitoring monitor your inference tables for any of the data drift or data performance. So as long as you have the inference table, have the input data and predictions there, we'll be able to help you monitor that. On top of that, there are a few functionalities or features I'd like to mention that is out of box, automatically done for you on Databricks if you choose to enable it. So anomaly detection, you can easily monitor the data qualities of all the tables in a schema. It automatically accesses the data qualities, specifically evaluating the freshness and completeness of the table. So freshness means that they're tracking how recently the data has been updated and flagging stale table if the updates are not up to date, it's delayed. And completeness are talking about we're checking on the table to see that if the ETL pipeline has loaded all the rows into the table. And these insights are populated into the health indicator. So you can have the glance of the health of your catalog with one dashboard. So health indicator is enabled at the schema level, and it will show up for each single table that is under that schema. As I mentioned, this is the dashboard that is automatically generated when you run the anomaly detection for the first time. And the dashboard will populate the insights for your scan schema. And data owners can then use this dashboard to see, okay, what do I need to quickly react on? Can I set alerts when I see any of the tables being stale? Can I tell somebody to keep up the ETL pipeline to make it up to date? And it's also critical for data teams to understand what kind of sensitive data has been captured in the tables, right? So data classification automatically classifies and tags the table in your catalog. And you can get alerts when the new PII information is caught in the column. And on top of all that, this is also automatically generated. So you can have this dashboard created out of box within Databricks platform to help you present the classification results. It shows you the number of the tables that has been classified, the distribution of different classes of this catalog, as well as over time as a time series table, time series chart, what the classification is looking like.
Thank you. So we'll just go wrap up into the outcomes and next steps. Obviously, we have a lot of work still to do in our monitoring approach, but we've got the minimum product in there at the moment. As a result of this project, we now have a foundational capability to ingest and combine our Datavault data assets and other Lakehouse data sets. For us, this will support quicker and less complex access to data in Databricks for our team and other analysts across Lifeblood. And it will also reduce context switching between T-SQL and PySpark and Spark SQL for teams that have to use both. A key capability that we're able to deliver through this work is point-in-time views and materialized views to support fixed point-in reporting requirements, which was not a capability built into the Datavault warehouse at the time. And quite importantly, this provides a clear lineage and a single point of integration between Azure SQL Datavault and Databricks, as if we went down some of the other approaches would have multiple points of entry and it would be really hard to control and manage. So with all that in mind, what are some overall insights after completing the stage of our Databricks journey? I mean, we always take it as have a plan, but be flexible. It's a fast-moving platform. So when we started our design for making Datavault available in our Lakehouse to now, we've adjusted our approach as new features were added and enhancements were made to the platform. It was really key for us to assess our requirements and our constraints, and particularly the limitations of what the team could achieve before considering building custom. And what worked really well for us was to build with what we had available now. And the team we had available now proved that it worked and would bring value, but not over-engineering the solution, as we had reason to believe we may be able to replace some of that complexity in the near future. Thank you for your time and attention.